today we're not going to lecture, well, we might lecture, but we won't lecture about the material in the class. Today I want to talk to you about the project. I know probably your mind is very far away from the project because the assignment is due on Friday. So, but if you can sort of pull yourself away from our three Russian friends and get back to this for a minute. All of you, of course, have chosen project papers. Everyone is stabilized on a paper that you chose yourself or that I sort of suggested you look at. And everyone is set, essentially, at this point. And of course, you spend some time looking over these papers, so you have at least some idea of what these papers look like. You probably felt a certain amount of confusion, I guess, and I don't know, hopefully not too much panic, but definitely some sense of, okay, what are these people talking about? And that's normal. These kinds of papers, that's going to happen. And part of the goal of the project is to try and demystify what the paper is trying to say. And so I thought we'd do a sort of a live demo of what you might have to do to deal with the paper, and to keep things fair, since I didn't want to pick a paper that I already know very well because then I would be cheating. I decided I'll just pick a random conference. This is SODA 2013. The reason I picked it is because they have all the papers available online, so it's easy to pick one. So I thought we'll just go through. This is something that you may have done. Many of you may have gone through a proceeding such as this to sort of figure out papers. How many of you did that? Look through a conference proceedings to find papers? You can raise your hands higher. It's okay. I won't bite. How many of you? Okay, those of you who did not raise your hand, how did you find the paper that you're presenting?
Start with an author.
You started with an author and you went from that direction, so you had some author in mind. How did you figure out that author? You knew something about their work, and you
suggested them.
Ah, okay. Okay, and then you went from there.
Yeah.
Okay, what else? Were there any other methods? Yeah.
Just Google Scholar in general, just start searching for topics that you're interested in.
But what did you search for?
Like we were interested in hashing, so I started pulling.
Okay, so you went through that, and yeah.
Asked my research professor to suggest some that are relevant.
I know some people did that. Yeah. Okay, so you had a couple of different ways. So through this process, either by searching or by skimming proceedings, you got to some paper, right? And so let's pretend that we're skimming right now, and you want to pick a paper. So there are some 150 papers in this list. They all have PDFs. So I'm going to just go slowly through this. And if you see something that seems, okay, let's stop, we'll stop and we'll look at that paper and we'll pretend if that was our project paper, what we would do. So I'm just going to go slowly through this. When you want to call out something, let me know. Why is this not? Ah, okay, it just didn't refresh very quickly. Okay, so we were here. So let me know whenever you want me to stop. This thing decides to refresh. Why is it not refreshing? Come on. I'm not connected to the internet. That's convenient.
That would do it.
Sorry?
That would do it.
That would do it, wouldn't it? Luckily, I'm smarter than the Uconnect server because I have a backup option. Except that I can't find my internet bar. So where is my network now? Oh, because it's trying to connect to your own. Don't do that. Your own doesn't work. Not anymore. I have a paper saved for this exact eventuality, but in case I still wanted to give you the chance. I did look at that paper yesterday night, so it might be considered cheating. So. Okay, fine. This is not going anywhere. Okay, fine. We'll have to go with the paper that I found last night. Okay. So this is a paper that I dug up for some other reason. I didn't read it very closely, I promise. I don't know much about this, I promise. Well, I know a little bit, but not that much. But this is a paper that, so let's say for some reason, you chose to present this paper. You saw approximation algorithms. Okay, approximation algorithms, you learned that in class. That seems like a reasonable topic. And then you saw a bunch of other words of that. I've got 5 minutes for the deadline, let's just choose this one. And you agree, you two see your project partners and you think. So how would you go about reading such a paper? Right? How would you approach the problem of what you need to do for the project? So first of all, what do we want to do in the project? So that's, I guess, the most important question. And what we want to do, you have to remember that every paper try to make it smaller to fit. Okay. thing to remember is that every paper you ever read, and this is true for the paper you're going to pick in this class, this is true for any paper you might read for some other class, this is true for papers you will read if you're doing a research project. Every paper has a backstory, right? It has a context. It has a universe in which it lives. It does not live all by itself. That is the first most important thing we need to understand. If you try to read a paper with no knowledge of its backstory, of its context, of the history of the problem that it's looking at, you will only be able to get a very, very vague, low-level or weak understanding of what the paper is trying to do. Okay? So for those of you who are used to reading papers, this might not come as news, or it might. For those of you who've never read papers before, this is something that's very important to keep in mind. Okay? So there's always going to be a context. And almost the first thing you have to do when you start reading a paper is try to understand that context. Now, if you think of the timeline, so let's think of now the present as somewhere, today as somewhere right here. And this is the past, right? So if your paper you've chosen, and so, I normally said we don't want to go beyond 1980. So let's say this is the... If you chose a paper that has been heavily cited, that somewhere is here, what do you expect to see about its context? You might, but you may not see much about what happened prior to the paper. There may be some amount. Since computer science as a field goes back to, I guess, the late 60s, the early 70s, this would be considered a fairly, young time in the history of the field. So you might have some context in the past for why this paper is looking at whatever problem it's looking at. Or you might not. But what you will hopefully have is a lot of context for what happened after this paper was presented. Right? After this paper was published, what happened after? What was the impact of this paper? And that's something that you will want to ask yourself as you read this paper. What happened after? So there's a whole, after question here. And it's possible that nothing much happened. It's possible that things were quiet for a long time and then suddenly something happened. All of these things are possible. That's one thing that's going to be your job to tease out from the paper, from looking at the citations. And that's where a Google Scholar is often very useful, because you can look at which papers cite this paper, so you can get a sense. Right? You're not going to read all of them in as much detail, but you'll read them very briefly to get a sense of how they look at this book. Of course, if your paper was somewhere closer to today, say in the last few years or so, then you may not see much of a context for what happened after this paper was written. It might take a while for its effects to play out. But you will have a lot of history that led to the writing of this paper. Usually. Okay? And that's going to be your job to figure out. What was the line of thinking that led to this paper being written? Why did the authors want to write this particular paper? What were they trying to deal with that has been part of the history of this work? Okay. And again, depending on the paper you choose and what period of time it lived in, it'll be one of these things. And of course, it's not just chronological. You could have a paper that's very old, that still was a culmination of a bunch of work and sort of ended a problem. You could have a paper that's very new, that still has had major impact because it started off something brand new. It depends. The point is, these are two different lenses you can apply to understand the context of a paper, and you need to figure out which one that is, or how it is for the paper that you're reading. Okay, that's going to be very important. And again, I'm not saying you have to do this in order, but it helps to understand these things. Because what you're really asking is, one of the first questions you're really asking yourself is, what is the problem being solved? You'll be surprised how, in many reports, and many times when I'll have a student present a paper to me in my research group, right? They will focus on the solution. What they're not focusing on is what is the problem itself. And that's something that you need to do. What is the problem? Forget about the solution. What is the question? That's probably the most basic question you can ask yourself. So what is the question? Okay? what is the question that this paper is trying to look at? Do not worry about how it does it. Really don't. Because at some level, that's not yet the point. Again, this goes back to understanding the context. There is a context, and that usually means there is a problem. Not a problem as in something difficulty I'm having, but a question, a research question that's being asked. And this paper is trying to answer. What is that question? If you can't answer that, you're going to have a very hard time explaining the solution. Okay. And this is often something that, in a lot of papers, the authors will, by necessity, they will spend a lot of time discussing the solution because they think that's cool, because they think that's why the paper is a valuable paper. That's what the authors think. That's not what you have to think. Okay? You have to understand what the question being asked is. Only then can you evaluate whether the authors have done a good job or done any job in trying to answer that question. A lot of papers will be, oh, this is the problem. Oh, here's a solution. And if you look very closely, you realize the solution does not actually solve that problem. But because it's all covered in words and text and experiments or theorems or whatever, you can't really tell. So it's your job to ferret that out. Which brings me to another point. Every paper is selling you something. It's selling you this wonderful piece of work, this magnum opus. You don't have to believe it. You can listen to it. You can evaluate the claims, but you don't have to buy into it. Again, many times people will present a report in a paper and they'll say, well, this paper does blah. And I'll say, really? So they, yeah, the author said so. I said, but are you sure? Have you, is there some way to verify what they're saying? And then total silence. I'm not saying authors are lying, they're not. But they will, in any piece of text, and this is something you learn when you do critical reading in say, a humanities class, right? People are always writing a piece of text to shape things a certain way, to focus your attention on something else. Like, don't look there, look here. This is where the shiny stuff is. Just because they're telling you not to look somewhere else doesn't mean you shouldn't. Again, it's about context. There is a context, there are some set of questions. The authors are looking at one question. There is a question to ask. Is this the most important question they should be asking? Should they have asked that question? Should they be asking a different question? You may not be able to address that point in your report. This is something that a reviewer for a conference does, and since you're not experts, you're unlikely to have that kind of broad enough perspective to see that. But if you can spot it, do so. If you've been reading, if you understand the context, you say, well, this is clearly a question that people should be asking. They're not asking that question. You can add that to your report. But you don't have to. But it's good to keep in mind that the authors will guide you in one direction. They will the good authors do it very carefully. So it seems like, yes, of course, this is the next step. And of course, this is the next step. And of course, their answer is the right answer. It's a very clever process of marketing. It makes you feel like it's just very natural. And it's good writing. But be aware that it's happening. Every paper does this. Every paper I write does this. This is how you create a story. And they're telling a story. You need to understand what the story is. Okay? Every paper is telling a story. Okay. And another thing that in theory papers you have to understand is that in a lot of papers there's a problem, there's a solution. That's not always how a good theory paper can get written. Sometimes the whole paper is, well, there is this problem, there's a solution, it uses this particular tail bound. This whole paper is about writing a better tail bound. There are entire papers on a better turn-off bound, for example. I don't think any of you have picked one of those papers, but there are papers like that. In other words, these are papers that try to improve a technique that's used somewhere else. Recognize that fact. This paper is not about solving this problem, it's about improving this analysis. That's fine. There are lots of papers like that. There's nothing wrong with a paper like that. It's just that you have to recognize that's the contribution. The contribution is not we took a problem and solved it, or we took a problem and solved it better. It's more like we took a problem, we looked at the solution, we looked at maybe 3 different solutions, they all use this analysis tool, we're going to fix this analysis to make it even more powerful. So it will improve them. Again, they will say something like this. Look for the clues that they're saying something like that. Understand what they're doing. Okay, so let me recap that point. What I want to say is that there are different kinds of And this could take a long time to list out, but let me list out some classic examples, right? So one is, old problem, new solution. And this could be better time, better space, better something, some kind of resource, better approximation guarantee, less use of randomness, whatever, some kind of better something. This is probably the easiest kind of paper to understand what the context is. There's a problem, there's a solution, there's a whole line of solutions, ours is better. And here's why. There was n squared, there was n to the 3/2, there was n to the 1.2, oh look, we get n log n. Those are very straightforward. A little less straightforward, but still kind of, not too hard to understand, would be new problem. It could be, brand new. In other words, no one has ever asked this problem before. So then the whole question, a lot of the effort in the paper is, how do you take a problem and model it in a way that you can apply algorithmic ideas to it? Right? So modeling is an important part of this paper. So then we'll talk about, there's a modeling issue. In other words, how do you take a problem and abstract it as a theoretical problem? So take this problem of transportation and think of the nodes think of the cities as nodes and the roads as edges. Oh, we have this problem we'll call a traveling salesperson. That's a modeling step. Okay. It could be a modification of an old problem. So, people have been looking at how to do vertex cover in general graphs, and we know it's NP hard, and there's a factor 2 approximation, and we don't know what else to do. Let's assume our graph is a tree. Can we do any better? No one would write a paper on this. This is a homework problem, or will be. But that's an example. You change the problem in some way. Let's assume our graph has tree with 5. If you don't know what that means, don't worry. It's a particular kind of graph. Let's assume our graph has no cycles in it, or something like that. Or our graph is planar. You can change the problem in some way. So that would be another kind of thing. Okay? So modification of an old problem. You could have, as I said, a new analysis. You take a problem, you take a solution, and you analyze it better. Often this means that someone had some analysis, they said, okay, we have the solution for this problem, it runs in n squared time. And then new paper goes like, well actually if you look at your algorithm very carefully and do the analysis very carefully, it runs a lot faster than new paper. So it's a new analysis. So the problem is old, the solution is old, but the analysis is new. Sometimes you have, and I don't know if anyone has picked one, you have lower bounds. You cannot do better. So it's a negative result. It says, no, everyone has been trying to show that you can get an n log n algorithm for matching to finding longest common subsequence. We show that this is not possible. And here's our proof under these assumptions. And so there's a lower bound result. Okay? Now, and of course there are now many combinations of these things. You could have a paper that does all 4 things in one. It'll have, it could invent some, it could look at some old problem, come with a new solution, prove a lower bound saying you can't do any better than the new solution. It says, well, because of that, let's try to change the problem. Let's get a new problem and say, we can do some upper bounds for this. And in fact, we can use this analysis from someone else, but their analysis was weak, so we're going to analyze it even better. All of these things will show up in one paper. So I'm not saying that any one paper will do only one of them. You will see these patterns appear. So you should look for them. Okay? So I'm just curious, are there papers that you selected, except I don't remember all the papers right now, are there papers that would not fall into, that would not have major elements from one of these 4 cases here? So I'm just thinking of them now, off the top of my head. These are basically, they cover a large fraction, but I could be missing something. Anyone? Any paper you've read that does not fall into this kind of category? Okay, so either it doesn't or you're not sure yet. That's fine. So it helps to understand these things when you start looking at your paper, to know what kind of paper it is. Okay. And of course, in all these papers, some of them are going to bring in, new kind of mathematics. They're going to bring in old mathematics from other papers. They're going to, let me get to the next one. Okay, so now once you have the kinds of papers, you now have the actual, now you understand what problems being solved. Hopefully you've got some categorization like this, you know what they're trying to do. Then you actually get to the solution they're producing. Okay, so that's the next point I want to talk about too. So the kind of solution. And this is where it gets really hard, and this is where a lot of the time is going to be spent. Because you're going to be trying to understand these fairly technical papers. You're going to get lost a number of times. You're going to see things that each step follows from the previous step, but the whole thing doesn't make any sense. Right? You can follow the algebra, but you don't understand the bigger picture of what's going on. And that's again normal. That's how it often is when you're reading these papers for the first time. It's helpful again to understand the kinds of solutions people come up with. Right? So your typical paper that you might read might look like this. So you have some main theorem that you want to prove. Okay? Or the paper wants to prove. It says, okay, to prove this main theorem, we need these, these three lemmas that have to work for this to prove. That's L1, L2, L3. Requires some very specific case analysis using some boring induction argument that goes for 3 pages and is ugly. But it turns out you can borrow some of that analysis to work into lemma 2, and lemma 2 gets proven that way, but lemma 2 is in this other piece which you get from some other paper here. Then lemma 3 you have to prove from scratch, and you just do this, you bring this new magic trick. I can't draw a rabbit, so I'm just going to pull a hat here. And you pull a rabbit out of a hat and you put it here, and it just seems like magic, but it somehow works. And then you put this all together, and then you get the theorem. And because I wrote this paper 5 minutes for the deadline, all of these are going to be randomly permuted, and not from this nice one. So that's going to be the problem. That most papers and most theorems have a structure. They have a structure that looks something like this. It will not be written that way in the paper. If it's a good paper, it will be. Most papers are not good papers, sadly. It'll be kind of scrambled. The authors would have had one thing in mind when they wrote it. And believe me, this happens all the time. 1 year later, they'll look back at their paper. I'm not naming names here. But they look back at their paper and they're like, oh my God, what crap this is. I should have written it all this way. I have to rearrange it. Okay? The thing you have to understand is when you're looking at a paper and you're now looking at the solution, not the problem, because you move past those previous steps, you have to understand the taxonomy. So in fact, again, what you should be doing is things like look at the theorem statement, skim the proof till it says, oh, we need lemma 3.1, so make a little arrow to that. Make a little diagram like this, looking at the dependency structure. Okay? Don't actually look at the proof itself. Just look at the dependency structure among the little pieces. Try to draw a picture like this. And then slowly start working your way back up to try and understand the different parts. Often what you'll find is that in these complicated proofs, there's going to be 1 or 2 important ideas. There will be an idea somewhere buried in the proof of lemma 1, which actually makes the whole paper work. If the paper is well written, the authors would have highlighted this point. Most papers are not well written. And they will not have highlighted this point. And you may have to go find it. If you can find it, that's really good. Because then you can really explain, this is the key idea that makes this paper work. And that is all you have to somehow be able to say, this is what makes this paper work. And in order to do that, you're going to have to know what came before. You're going to have to know which techniques are being borrowed from earlier papers. Because sometimes people don't quite always carefully cite this. So sometimes they're going to hand wave, oh, we apply a Chernoff-Bound. They're going to say, okay, I know that, that's the Chernoff-Bound. It's not important. And you're going to have to figure out what's important, what's not. Focus on the important things. So, in other words, reading a paper is not a linear thing. You're not going to go line by line by line through it. You're going to jump in, you're going to jump out. You're going to find pieces, you're going to put them all together in something. Okay. There will be more things that come up, but I think I want to stop here and then apply these ideas to an actual paper, the one that I just showed you, and then we can see what happens. But before I do that, questions? Yeah.
So, the paper is published. Is it safe to assume that the author, if they derive a lemma from some other paper, is it safe to assume that they did so correctly?
Well,
I mean, like, do you just take their word for it that like you can derive this lemma from this paper?
you can be sure that they thought it's correct. Sadly, it it is not a once in a super red moon event that a paper will have a bug in it. It doesn't happen that often. I would be surprised if more than 1 or 2 of the 48 papers that have been chosen for the projects have a bug in them. I would be very shocked if any of them had a bug that was a serious bug. So there are bugs and there are bugs, right? There's a bug in an argument that doesn't break the lemma. There's a bug that breaks the lemma. And there's a bug that breaks the lemma and therefore breaks the theorem, and the whole paper's gone. There are different levels of severity. It is quite possible there's small careless errors, like a 2 becomes a 4 or a 4 becomes an 8. If you don't care about the constant, it won't matter, but there's some small careless mistakes there. Those are, you can, okay, fine. It's a constant anyway, it's fine. They might make a mistake where the running time is n log squared n, it should be n log cubed n. That's a bit more serious. But again, if they've improved it from n squared, it's not so bad. It's bad, but it's not like earth-shattering bad. Then there are bugs which just break the whole paper. That's a big problem. I think if you can find a bug that breaks a paper, that in my view would count as coming up with a new result yourself, and therefore all the added benefits of coming up with a new result yourself, and the class and the grade and everything will own. So if you can find an actual bug that breaks the paper, that gives you, lots of brownie points. So, but don't expect that to happen. And so, in other words, if you're reading a paper and you think there's a bug there, just like if you're writing code and you're convinced that the compiler's messed up somehow, most of the time it'll be your problem. About 95, 98% of the time. There's a very, very small chance it's not your problem with these papers. Especially if they've been read and cited a gazillion times, someone has usually checked over them. Okay? But I'm not saying it can't happen. But don't go in assuming it's going to happen. Don't go in assuming, okay, this doesn't make sense as a bug. I think the default assumption has to be that you're not getting it. And if after a long time you come and talk to me and this is not working, then it may go. Yes, you had a question.
I'm still a little lost as to what we were writing about. I understand how to read the paper, how to understand it, but I'm not sure what I'm supposed to write about.
Good. Let me talk about that then. Before any other questions? Yeah.
There's a measurements paper, like for example, if you compare to existing things and if you give a new upper type form also existing.
Yeah.
So in this case, like for example, how to kind of write a research topic with respect to what is the comparison of.
I don't understand. What do you mean?
Like for example, there are 2 measurement papers. One is an existing solution which solves an existing problem. There's another which they're comparing with that to give a better problem.
Sure.
Okay, so in this case, if you want to find a bug or something.
But why do you want to find a bug?
To give a better outer load.
You want to find a weakness.
Yes.
Okay, that's good. That's not. Oh, I see. So you're trying to go for the brass ring. Is that what you're saying?
Yeah, not exactly, but trying to find a way to give a better outer load.
Now you're asking how one does algorithms research, I think.
No, to how to go about such kind of papers where the measurement is between 2 existing approaches.
So maybe I'm not fully understanding. So there are 2 papers. They're both, one gives one bound, one gives another bound.
Yeah.
And you want to do what? You want to give an even better bound.
Yeah.
So there's bound, and you want to be here. So this is basically how algorithms research is. You're trying to get a better solution to a problem. So, and you're saying you want to do something better than what this paper. So one option is to look at them very carefully and see if there's a weakness in the analysis. Maybe they're loose, maybe they're sloppy, maybe they said, oh, we'll just pretend this summation can be upper bounded by blah. Because we can't, it's too complicated to analyze it any better. And you have a way to analyze it better. You may be able to do something there. Maybe the algorithm design is just somehow flawed. Maybe those 2 approaches are just completely, you should just not go that way and come up with a brand new strategy. There's different things you could try. Seems to me a different topic. You don't need to do that for the project. I mean, you could, but you don't need to. I mean, that's a discussion I think we should have separately about how you do algorithms research, which is another interesting question. That's not relevant, I think, to the project. Any other questions? Okay, so the question of, okay, that's all this is very good, you can read, blah, 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 but how do you write? Okay. So I have an actual guideline for the project. I think it's on the project guidelines page, which I would have shown you if my network was working. Where I described it, I've given a sort of an outline. So I'm a little leery of saying something different because I don't want to say something that contradicts what I had. Let me see if I had any luck with this. fine. No, it did not. Okay. This room is like a black hole. Are you all able to connect? Are you all having problem? People laptops, are you able to connect? Yeah? Sorry? Sometimes, yeah, that's the problem, isn't it? Yeah. Yeah, you should go look at the project page, which I do actually have a somewhat detailed description of what I expect to see and what kind of questions I want you to answer in the report. But let me outline. Okay, good. So I think I might be able to get it working now. So we don't want to see that. Say what? Okay, so first of all, basic brass tacks. There's a soft max limit. I mean, these are some minor details. You don't need more than 10. You don't have to do 10, but you know, again, you can. Okay, so these are things this is what I want to see in the report. So number one, you demonstrate an understanding of the results. In other words, you understand what the main problem is being solved is, what the main results is, and what the context is. You know, so what is the, you know, this is an approximation algorithm for this problem that is known to be NP-complete. You know, things like that. You demonstrate some understanding of the actual, you can give some, and I'll talk about this in a bit more detail. You have some high-level understanding of how the algorithm works. Okay, so first they take the graph, they divide it into 5 pieces randomly, and for each piece they do this and they recursively combine them, and then they show that this all works out. Something like that. The proofs of the key ideas, like I told you, you don't need to reproduce the lemmas. You should give some kind of overview, this kind of, you know, even a diagram if you wish, or some kind of flow of how the main results work out. And you decipher how to present and explain. Sometimes, you know, use the same format as a paper, or you choose to structure your report a different way. I mean, that's again up to you to decide whether you want to follow. And I mean, I don't really think that's helpful to follow the paper outline, but just sort of think, okay, this is what I would expect to see is something like, here is the so let me write this down. So there's again, you should read this in general. Let me outline what I would expect to see. So what do I expect to see? So number one, what is the problem? What is the context? Which is another way of saying, why is it hard? Okay? Number 3, what is the main result of this paper? And I should emphasize that most papers have more than one result. They'll have a main result, they'll say, okay, this is our main theorem, we show that in graphs with 3 with 10, you can solve the vertex cover in time n to the 10. Oh, and by the way, as a corollary, we are able to show that for planar graphs with branch width y, you can also do this by the same technique. And for graphs of girth 3, you can do this, and there's a bunch of side results. Okay? So each paper will have more than one result. You will decide where the main ideas of the paper are. And you can mention these results aside without having to go into detail. That's your choice, how you choose to explain it. Okay? So you'll have the main result. You'll spend some time talking about, you know, how the main result was shown. In other words, what are the key ideas? And to give an example of what it means for something to be a key idea, right? When we talked about approximations, for example, we talked about vertex cover, right? And you're saying, okay, we have this true approximation for vertex cover, or we have this Christophanides heuristic for TSP. The ideas there were the following, right? So, okay, we want a lower bound on the optimal solution for the traveling salesperson problem. The minimum spanning tree is such a lower bound because every path is a tree. This is an idea. It's not for, if you ever read the original paper, it would not necessarily, there would be a theorem saying the cost of the MST is less than equal to the cost of the TSP. Or they may not even be said, it just may be mentioned in passing. But that's the idea. That's what you want to bring out. Imagine if you were teaching this result to someone. You wouldn't just recite the lemmas and theorems. You would say the key idea is that the MST is lower bounds the cost of the TSP, and you can take the MST and make a tour from it. Second idea. Putting these two together gives you a two approximation. So now you have two key ideas that give you the result. There is of course the actual proof that this works, the calculations, but they are driven by the ideas. And that's what you have to do. Okay? So the main result, the key ideas, and then again, now if this is a paper that has had a lot of follow-up, what's the follow-up? So, depending on the paper you pick, as I said, this part might be quite big or this part might be quite big. It depends on the paper you picked and where it came from. So you will spend some time on that. And then of course you'll have a bibliography. So what I expect will happen is that this part here will take anywhere from possibly, at a minimum 1.5 pages or so, up to 3. So let's say 1.5 to 3 pages for this part, depending on the context, depending on what you want to say about it, depending on whether you want to give some illustrations of simple results and how much detail you want to get into. You'll have to state the main result, and this will probably take a good, for any reasonable paper, it will take a good, probably 4 to 5 pages to explain this part. Okay? And then there'll be follow-up. And again, if the paper is very brand new, then there may not be a lot of follow-up. But you can have a general discussion at least to explain, what's interesting about this. And that might take up to a page or so. Okay? So about a page or so. And then there's bibliography, which is not counting a limit. So you can actually finish in less than 10, and that's fine. I'm not holding you to it. You have to get to the last line of the 10th page. But this is how you expect things to break down. Question?
So I understand that we're supposed to explain that we understand the paper, but I sort of have trouble seeing how you distinguish between just copying what they have on the
Okay.
paper.
So I could sit here and take the notes and recite them to you. The notes are, so I do a lecture on approximation, I could just recite those notes to you. That's equivalent of copying the paper. What I do, or what I try to do in lecture, is not just recite the algorithm to you, but pull out what I think are the interesting ideas from that algorithm and explain those ideas to you. And then explain the algorithm in the context of those ideas. That's what I want. Not just copy what's written there, but pull out. You will see with these papers that there will be a whole load of math with very little insight. Okay, we do this, we do this, we do this, with lemma 1, lemma 2, lemma 3, here, done. And we're like, okay, but I don't know how they got to this. I mean, I see how each step follows, but I have no idea what just happened here. In the process of trying to figure this, you'll have to stare at those lemmas one by one. You'll say, okay, what is this lemma really saying? You'll take a lemma and you'll translate in your head into something. And we're going to do this now as an exercise. We're going to sort of walk through a particular paper and see how this works. And then you will have to pull out something more insightful from what exactly is going on. Okay? This is one of those things where as you start working with it, you will start bumping into problems, and then you will all come and talk to me, and then you will see how to unblock yourself, and that's what will happen. So you will be talking to me a fair bit, I expect, about this. Yes?
So for follow-up, will we just see like what kind of papers have cited the paper that we're researching?
Yeah, some sense of, okay, what was the impact of this result? Right? Again, it's all about context, right? If you want to understand the paper, you've got to understand its context. What did this paper lead to anything? Has it ended a line of work? Has it opened up a line of work? Right? And that's something that you will be able to assess by just skimming the abstracts or just skimming the portion of the other papers that refer to this paper. Right? You don't have to read those papers in detail. There's no way you can do that. But you will skim them and you'll say, okay, that's where the cites is. What does it say? They might say, oh, in spite of the horrible claims made by this paper, we can show them. And if all papers say, okay, this paper said something that was very controversial or whatever, things like that. Most of them will say, okay, this paper did this, and we can now follow up and do that. And then you need to explain that. Any other questions? I want to go into the actual paper and sort of apply these principles, but before I do that, are there any other questions about this? Again, this is all very abstract. It will be helpful to see this in the context of it. Okay. Maybe let's take a minute or two. Let's take a break. We'll come back. 2 minutes. think you're confused because you're expecting some kind of stronger statement when I'm asking like this. You're trying to be clever. You're expecting something very good that's going to come out of this. It's very simple.
I feel like what I showed,
We should read that as well. That's probably my last one. Sorry? All right. Shall we start? Okay. So I gave you this kind of high-level overview of what, how you might go about attacking the paper and how you might go about producing a report on it. So I thought I'd try to give you a live demo of what that might look like. Now, of course, it's necessarily going to be a lot faster than what you might do, because of course you're going to spend 2 months working on this, and I'm trying to give you in half an hour, 35 minutes, an entire span of what you might do in 2 months. So obviously it's going to take you a lot longer to go through your papers than I'm going to go through here. But if you think of it as a speeded up version of how you might go about attacking things, I'll try to illustrate how it might work. I mean, I could pretend to, and I tried this last time to try and read it the way you might read it, but that's not going to work because I have too much crap in my head, and there are things I know that I can't unknow, so it'll be hard to do that. But let me at least give you an illustration. Please feel free to stop me when things are not making any sense, or just it's completely you have no idea what's going on in terms of the process of how I'm doing this. Okay. So the first thing I said was, every paper has a context. You need to understand what the question is that's being addressed, and of course, don't believe in marketing. In other words, recognize that there is a shading, there's a story being told there, and recognize the story. So maybe a fair way of saying this is that, is understand the story. Okay. So let's take this paper that we had in mind, and again, remember what you want to ask is what is the context and what is the question being addressed. Okay, so this is the paper. Right? So the approximation algorithms using hierarchies of semi-definite programming relaxations. And again, you probably may not know what all of these things mean, and that's okay. Like I said, if you start going on every rabbit hole every time you find a word you don't understand, you will have the same problem in depth first search actually. So it takes forever to find anything. So you should learn how to sort of skim the surface of a paper. And so let's start with it. So it's always good to start with the abstract, although personally I don't read abstracts of papers. It's just, if I'm going to read the paper, I'm going to just read the introduction anyway. Like your mileage may vary. Let's just start from the beginning, because the introduction has a good story. So, so I'm not going to read this, but you know. So, what it's saying was that there is this thing. I don't want that. So this is in fact is a storyline. It's saying there's something, there's a blah. We don't know what the blah is, SDPs will call it, we don't know what that is. Has been an important tool for designing approximation algorithms. That we know. Hopefully we've been hearing about approximation algorithms. So we know what space we're living in. We're in the space where we're trying to find, not exact but approximate answers to problems, and this is supposedly some important tool. Okay? And it starts off by pointing out the seminal work, make a mental note, saying, okay, this is, so let me actually do this. I'm going to start making some notes here. So I'm going to just start scribbling mental notes to myself, and there's something you should do on paper when you're reading paper, so what's an SDP? What is this Gomez-Williamson thing? There's a reference for it, so you can dig it out. Okay, so go back. Series of results. So the authors claim that this is an important tool, and they're justifying their claim by giving you a bunch of citations. Okay, there seems to be a bunch of problems. I could track them down, but I'm not going to worry about this right now. The SDPs lead to this. Approximately are there. Basically, what they're saying is supposedly awesome. It's the translation for those words there. They're essentially optimal, and for there's something grammatically wrong here, but anyway, okay. So one possible avenue. Okay, so this is where they might be leading into what might be about to happen. One possible avenue of improvement at approximation side is the use of so-called SDP hierarchies, which tells you this is a jargon term. So what's a hierarchy? Well, they haven't been defined yet. Each hierarchy is characterized blah, 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 a bunch of stuff. Okay, so then you write a note, something called SDP hierarchies. Okay, and why do you want this? These hierarchies have the joint property that for some integer program, and again, you might not yet know what integer program is, so you put a note saying, integer program here. You've heard of linear programming maybe, or maybe you haven't. We have another word to look at here. Integer program, nth level hierarchy is equivalent to the original integer program. That seems somewhat important, but you don't know why that's important. It seems like they're saying it for a reason, but you don't know idea what it's saying. Okay, maybe we should put this in our head. Now at this point you can say, okay, I have a bunch of buzzwords now that I don't understand. I can stop and go start reading up something on them. Or I can continue. That is up to you. Some people have a higher level of tolerance for uncertainty and they can just keep going. Some people are like, no, I need to understand every detail before I go on. You don't really want to understand every detail before you go on, but you may have a threshold beyond which I no longer understand anything that is happening. And I need to go back and read something. Which way shall we go? This is a choose your own adventure game here.
Onward.
Sorry?
Onward.
Onward. I have a suggestion for onward.
I support that.
You support. We have seconded. Onward.
I agree.
Oh, you agree? Onward. Okay. So I hear no one saying we should stop and dig into details. Interesting. Okay, good. Let's go onward. So we have a bunch of words. So right now, if we're reading this and again slower than I just showed you, we're thinking there are these things called SDPs that have to do with approximation algorithms. They're good for approximations. People use them to solve problems and get approximations. there is this thing called an SDP hierarchy that might be better in some way, and we don't yet know how. Okay, so let's read. So the quality of approximation. Okay, so now we're saying something about this quality, right? The quality of approximation of these hierarchies has been studied in the context of law, right? I don't know what that is, but they mentioned combinatorial. Well, so okay. I don't know yet if this is important, but I'm going to ignore this. There's been a series of negative results. Well, we know what that means. Starting, so these things do not yield good approximations. So wait, they're saying that these hierarchies were good, but they're not good. That's kind of weird. Okay, so we skip that. And then now they showed, this person showed an integrality gap. I don't know what that is, but this seems like a bad thing. You see omegas, you know there's a bad thing somewhere. This group showed that this is, again, bad thing, bad thing, bad thing. And they're not giving. So this whole paragraph says, these hierarchies are great, but there's a whole lot of bad news. Okay, so why are we studying this? So this is all bad news. Given that these hierarchies can be solvable, it is natural to ask, now we're getting somewhere, whether for any optimization problem, these yield improved approximations at a constant level. I don't know what a constant level is, but I understand that they're trying to say there were these SDP hierarchies that we thought would be good for approximations, but we got a whole lot of bad news, and now we're trying to understand, can they be good for anything at all? Now something is beginning to slowly go. Okay, they have something called SDP hierarchies that they want. Now you go back and look at the title again. Like, oh, now I see. So they somehow want to, the author wants to be able to use this thing to produce better approximations. And it seems like it's a really hard problem because of all the evidence they've given. And now they're going to hopefully tell us how to do it. So now we go back to our notes and say, maybe something to do with getting good approximations using this thing. So this may be what this paper is about. Again, we don't know. It's a tentative hypothesis about what this paper is really about. But that's our working hypothesis. Still, something tells us it's not the case. Okay? All right. So we go on. And again, of course, I'm lying to you by reading this linearly. If it were me, I would get very impatient. The minute I saw SDP hierarchy, like, what is that? And I would start skimming through the paper and I would go through and say, oh, this is it. Wait, I have no idea what this notation means. I better go back and read this. And I go back and forth. I would be reading this back and forth, it would just make you dizzy. So I'm not going to do that. But that's how these papers normally get read. So we come here and we say, okay, so there's one reason to expect this. There's something going on here. These actually are important lines, but you may not be quite ready to appreciate what they're saying yet. So if you want to skip it, that's fine. So I say more concretely, finally, something concrete. Okay. So more concretely, you propose the following heuristic. Given an algorithm which rounds an SDP solution, like, so there's something here. So I'll put this rounds. Okay. Analyze this algorithm under the assumption the solution is in fact a convex combination. So I don't know about you, but if I'm reading this and I've not heard this stuff before, this is getting very confusing. So to this end, we offer two. Now the author is now saying, okay, these are the techniques we're going to adopt, and you may not be quite ready to read this yet. Okay, but you can say, okay, what is the problem? As an application, we investigate two problems for which the status of the approximation is open. For both problems, we should. Okay, so now we have an actual problem statement or a solution statement. We provide better approximations for two problems, maximum independent set in 3 uniform hypergraphs and graph color. So now we come down here and say, okay, so the problem being solved is max independent set in 3 uniform hypergraphs. And I may not even know what these things mean. And graph color. And what we're getting is a better approximation. Okay, so this is a little bit more concrete. We know what an approximation ratio is. We know what that means. We know that getting a better approximation means getting a better factor by which this algorithm is far away from the optimal solution. And that's what they claim to be doing in this paper for these two problems, using this SDP hierarchy thing. This is good progress for your first reading of the paper. You've already got some basic sense. You don't really know these terms, but you finally understood what the problem that they're trying to look at is and how they might be trying to go about dealing with it at a very, very, very high level. At this point, it might be a good idea to start looking at some of these terms. What is semi-definite programming? In fact, and you will find that for a lot of these concepts, there'll be lecture notes available. Wikipedia might be something you can look at. There's lots of things you can go and read to understand this. And some of these things will have been covered in class. We'll cover SDPs in class a little later on in the semester. So you'll cover some of the stuff. Okay? And then you can use that to sort of go back and get some background on these things. You will, but as you will see, the paper itself will define everything. But what it won't give you is the kind of background context that some lecture notes won't give you. Okay. So there's a bunch of stuff here. We start the problem of finding larger dimensional uniform hypergraphs, a bunch of background. So this is what I mean by giving context. So this is what the author's doing. They're saying, okay, this is what a K-uniform hypergraph is. So K is 3. It's a collection of sets of size 3 over a vertex set. An independent set is a subset that does not fully contain any hypergraphs. So this is a complete definition of the problem. Right? And this is the background. This is explored by so-and-so, and this is so-and-so, and this is so-and-so. And then at the end, you say, okay, in contrast, we can find an independent set of size this. Why is this good? Because the previous bound was this. This was the previous result, and this is the current result. So you're not getting anything. This bound is bad, this bound is good. That's basically what it's saying. Second problem, coloring 3 colorable graphs. Long history of study. They have this bound here, then they have this bound here, and then finally this result is improved, is given this bound here. And what do? We get this bound here. Oh look, this bound is worse, this bound is better. There's an improvement right there. Again, how much improvement, whatever, that's fine, but you can see the improvement. So they're giving an approximation algorithm. This was the previous approximation, this was the new one, and this number is better than that one. So okay? And there's related work, and we can ignore all that stuff. Now this is often handy. A good paper will have some kind of organization. So it'll actually help you sort of understand how the results are going through. Let's say, okay, we'll define all these things, social properties, we'll give sections 3 and 4 this and this respectively, which means you can now focus your attention. Okay, I don't need to look at section 4 right now, I can look at section 3, or whichever way you want to do it. So a good paper will have this. It doesn't have it try to figure out what it is, what the organization of the sections are. And this is your first reading of just the introduction of the paper. You've got some rough ideas of what's being done, you have some landscape of the paper, you have lots of things to go on. Okay. This is your first section of the paper. You'll have many more like this. Any questions so far? Again, I went through this really quickly. This would be normally it would take you maybe a couple of hours, not 10 minutes it took me. Not normally how long it takes. But any questions so far about what you've got so far? Okay, let's go back to our guidelines. So we said we want to understand the context of a paper. Can we answer at a very crude level, and this will be refined over time, what the context of this paper is? Can we say now, based on what we just read, what the context of the paper is? What do you think? What is the context of this paper? That we just skimmed very quickly. What are some, yeah, go ahead.
Showing the hierarchy, what was it? I never forgot the word.
SDP, yeah, okay.
Can be used to prove approximation.
Right, so the context is basically approximation algorithms as a whole. We know what these are. These are for solving hard problems. An approximation algorithm allows you to get close in a provable way, and we've seen this already. And so that's the overall context. And what the question being addressed is, as you said, how you might use some particular tool to get better approximations than people have been able to get before. Okay? So you have some very crude answers to these first couple of questions. This paper appeared in 2007. You don't know that, but I happen to know that from this paper. And so if you ask, what is this a paper where things led up to it or things happened after it, we're not quite ready to tell, but we can tell that a lot of things happened before it. Because the author mentions all this work on semi-definite programming and all these results. This is a bunch of work that led up to this. And so they're trying to answer the question of, well, we can only go so far with SDPs. If we do these extra SDPs plus is what they seem to be, can we do any better? And that's the question they're asking. So that gives us a very first cut approximation to these questions being asked here. What's the problem being addressed? What's the story? And what's the context of the story? So what kind of paper is this, do you think? If you had to put this category, where would you place it? And again, it doesn't have to be an exactly one, but where would you be closest to in your mind?
One problem.
One? So why would you say that?
because they are saying it has already been used, but then had some implications. They are trying to make some modifications to it and address the same issues.
So there are old problems, free hypergraph coloring and graph colors are old problems, and they want to give a new solution. Is there something better? What is the better thing they're trying to sort of
I
produce?
think they are trying to use the hierarchy.
I know, but no, what I mean is in terms of what is the improvement, the actual improvement they're trying to get at.
Approximation, better approximation.
Better approximation, very good. So it's trying to give a new solution that has a better approximation. There's also something else that's going on here.
Lower bound. Lower bound.
Are they giving lower bounds in this paper?
Well, better runtime, I guess.
Sorry?
It was better runtime.
Right, but you said lower bounds.
Yeah, I was wrong.
Okay, no, but they might be. We haven't looked. But it may be. So in fact, let's go back and look. Does this paper have any lower bounds? It doesn't seem to say so. But you never know. So if you skim the paper, actually I don't know if any lower bounds. I would doubt that they do, because these are very hard problems to prove. If you're wondering if I'm reading this, I'm actually not, but I know what I'm looking for. So. Sometimes they put lower bounds at the end, because a dirty secret of algorithms research is that lower bounds are not as cool. It's hard to sell a paper with all lower bounds, because basically if you're just giving bad news, no one likes to talk to you. You're not the fun person at the party. So usually they hide lower bounds at the end. So it's a good place to look at them. Unless the whole paper is about lower bounds, then you're really not a fun person at the party. Okay, so there's no lower bounds in this paper, but it's good to check that. Okay. Is there anything else that's going on here?
Maybe a new analysis, because the previous analysis said this is bad way to look at things, but they say with this kind of improvement we can actually do it better.
Yeah, so there was this HTTP and they said that is limited in some way, but we're going to do something different to it, and so it might be a form of new analysis as well, right? So we already know that it's got some flavor of a better algorithm for a problem that gives a better approximation. It's got some flavor of a new analysis. It doesn't appear to have any lower bounds. It doesn't appear to be solving any new problems. It's solving in fact old problems. So we get some idea of where the contributions are coming from. So that's going to be important. All right. We're not ready for this yet because we haven't actually gone to it. But just reading the introduction, we get some rough idea of the answer to these first two kinds of things. And again, it depends on the paper, it depends on your mileage, but it really varies. Okay. All right. Shall we try to wade in to the thicket? Into the morass of lemmas and things? A good paper will have definitions. There's always a definition section. A good paper will have to do that. It will try to make things relatively self-contained. I say relatively because relatively depends on the expected level of the audience reading it. These are research papers. They're written for a certain audience. That audience is not this crowd. So they're going to be very terse in their definitions. But they have some, so for example this, the Lasserre hierarchy is a sequence of nested semi-definite relaxations for 0-1 polynomial programs. So far we have no idea what any of this means. Right? These STP, so the first thing you're going to have to do is to understand what SDP is. So there's a time when it's okay, I cannot go any further till I understand what SDP is. So I'm going to go back to my notes, which were here, and I start looking up. So I go to, so let's see. I think I still have my network connection. Ah, that's nice. So Wikipedia is good for certain things. Wikipedia is not as good for gaining intuition. So you can read the definition here. It's a linear programming problem. You have equivalent formulations. You can read these things, and there's a bunch of definitions there. This is what a semi-definite program is. You will also find it's useful to do things like this. There you go. Whole bunch of stuff. You will find these to be way more useful because they are written in a lecture form to teach you something. Okay? So you might, I don't know which of these will be good. Let's try one. Okay, this is an entire collection of notes. This is actually, well, my view is pretty awesome. I don't know what your view is. So then this is the definition here. There'll be a whole bunch of stuff here, and I think this is an integer program formulation, which we've heard of before. and you're going to find this. This is what is this? This is the STP, and then it'll actually explain, hopefully, what this is doing. I don't like these lecture notes. So, and this, you'll have to iterate this a couple of times. So. There, formula, good. Okay, this is not that good. This is very dense. So again, this is what you might decide to do. There's different ways you could go about doing this. This actually might be quite reliable. Yeah, so this is actually a bit better, at least in my view. So symmetric matrix is defined as positive semi-definite if it's got those definitions, okay? And then you'll have this, and then this is the definition of something. So again, this will give you the definitions. It won't give you the intuition, but reading the notes will help you gain some intuition as to what it's trying to tell. And again, this is where you're welcome to come and talk to me about these things. I have enough perspective on some of these things that I can help you with understand what's going on. This is a particularly hard paper as well. So I don't think some of the ones that you're looking at are tricky, but not all of them. So once we've understood what a semi-definite program is, we might be able to go back in this. But you might also find, they mentioned Lassé hierarchy. This is reference number 22. So what is reference number 22? So we go back and look at reference number 22, and it says what? Lecture notes. That's fine. So let's go back to our trusty Wikipedia and say, voila. Well, this is the actual paper. We don't want that. There's a bunch of stuff here. There's a bunch of notes here, scribe notes here. So there's a bunch of lecture notes you will find that will be useful. So what I would say is that lecture notes are often very useful to try and pick up on some of the concepts that you're having a hard time with. Again, Wikipedia will define them for you, but they may not give you the right feeling for what they really are. Right? Every animal has a certain nature, and all these are animals that have their own nature. And it's one thing to say an elephant has a trunk and 4 legs. It's nothing to sort of tell you what its personality is, what you want to learn about. So having done that a little bit more, again, let's go back to our notes. So we've done this. We've tried to understand SDPs. We've tried to understand these notions. We've tried to understand what SDP hierarchies are, and this will take a good probably about many days of reading and thinking and reading. You'll now be able to go back and look at the next section of the paper. And again, like I said, this one is particularly tricky. So. And then you might be able to go back and read this. And then again, there are definitions here. You'll start reading. There's a whole bunch of definitions. Most papers will have a whole bunch of definitions and some basic background. These are simple lemmas. When they say things like this, be very careful, because they're usually not. But but it's helpful to try and think about why these things might be true. Okay. This lemma is very specific. I don't want to jump into it right now, but you will find that it's often useful. And I want to see if I can get a good example of this. Lemmas are not usually that easy to. Okay, this would take a bit more digging into this paper that I don't think I want to do right now. You will find that it's helpful in any case when you see a lemma or theorem to try and translate it to English, to try and not focus on the details of these things, but try to see what they're saying. So in this particular case, okay, this might take a bit more time than I have right now to explain, but most lemmas usually have some higher level explanation. So for example, let's see. So this is a helpful thing, right? So this says, okay, this lemma says blah, 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 right? So we say we use the following notation for the tail bound standard normal. Nx is the tail basically from x to infinity of this distribution. So it's saying this how much probability mass lies in the range from x to infinity, which is the definition of a tail right there. So what this lemma is saying? This lemma is saying that this tail has a lower bound and an upper bound. And the lower bounds and upper bounds have the same dependence on s in the exponent, but they have different dependencies on s in the polynomial term in s. One way to translate this lemma into English is saying we can give a pretty good bound on what the tail of a Gaussian looks like. We can sandwich it between two terms and a little bit of extra stuff. And that's all you need lemma for. Lemma 4 in your mind should become we can bound the tail of a Gaussian distribution very nicely. That's it. You don't need to worry about any of the details. So again, this will not be obvious to you. I mean, I went through this very quickly. But if you look at the definition and think about what this is saying, you will find this higher level nugget which you need to keep in mind and not worry about the details. Otherwise you'll get lost in the details. And that's going to be true for all the other levels. Try to translate them into some higher level statement about what's going on. Because that's how we reason about these. Okay? So again, you'll go on again. So there's two sections of this paper according to there's finding large independent sets, and there's also section 4 which was doing graph coloring. You might choose that, you might decide that one of these is hard enough that you want to spend your entire report on one of these results. That's fine. If it turns out to be so hard that you can't really cover the paper, that's okay. You don't have to cover the entire paper. It sounds like this paper is using one technique to solve two problems, so you could just focus on one of those things. Since you hopefully have understood that from reading the intro and looking at the outline, that's a determination you can make, and I'll be fine with it. You don't have to cover it. So again, you have to decide based on the structure of the paper what parts you want to cover, what parts you don't. Okay. Questions? Again, I want to emphasize, I went through this really quickly. This is not the normal speed at which you'd be going through this material. Yes?
So if you were writing a report for this paper, would you, in your report, explain what SDP is?
I would.
Okay.
I would actually spend a reasonable amount of real estate explaining to the reader what an SDP is, not the quick way in which this is done.
Okay.
Because I'm trying to teach someone what's going on in this paper.
Okay.
If I were to try to present this paper in class, I never told you what an SDP was, you would have no idea what I'm talking about. So which is why I'm saying that 10 pages is not going to look so bad once you realize that you have to actually define some basic concepts that are not actually mentioned here. You'll have to define what an SDP is. You'll have to define what an SDP hierarchy is. You'll have to spend some time doing those things. And that's going to fill out your 10 pages if you're scared of that, how I'm going to get 10 pages filled out. Yeah. But yeah, think of it as this report will be used to teach a class on this topic, not regurgitate what's written. So you will spend a lot more time explaining and clarifying and saying, okay, this one sentence that they said that was very cryptic, this is what it really means. And it took me a paragraph to explain it. And that's good. When I see things like that, I'll be very happy. That's a good. They took the time to try and explain this one sentence and they really expanded it out. That's good stuff. Yes?
You answered it.
Okay. Yes?
So if there's a lot of math in the paper, for example,
And there will be.
there will be, do you just kind of give an overall view of this is the direction they're going, this is what they're trying to accomplish? Do you show much of the math?
It depends on the proof. So for example, there might be a lemma that says we want to prove this inequality. That this object is in fact a lower bound on the optimal solution. Here's a 3-page proof by induction. You don't have to reproduce that. If there's some interesting idea in that 3-page proof by induction, then you might say, okay, they want to show that this is a lower bound on this. This is not obvious at all, but they make use of this specific fact buried in page later. And then the rest of it follows by induction. You don't have to give the whole detail. Right? So your task is going to be to give details where you think it's important for the reader to understand and avoid it's like, this is just like too technical. The message of this lemma is more important than the way it was proved.
So kind of hand wave the messy stuff, but point out the key ideas.
Exactly. And the trick is knowing what's a key idea and what's messy stuff. That's the hard part, right? Is this a key idea or is it just messy stuff? This is where the context will help. Right? If they're using some prior results that use some technique, then it's not a key technique for their paper. Or maybe they're just recombining it something. So that's something that you're going to have to understand. That's where your understanding of the context will help. Yes?
For the report, do you want any specific format, like IPG format or such?
Not particularly. Anything will basically, I'll provide a style file, but just a general article style. I don't have anything specific in mind. Yeah, no double spacing, no huge margins. But apart from that. Yes.
You have like a LaTeX template?
I will give you one. Yeah. I'll put it up within a day or two. Yeah.
This covers details on the final report, but the intermediate.
Right. So let me go back to that because I have a note on that as well. Good. Very good. I'm glad you asked that question. Okay. So, I'm surprised I didn't mention the page limit. I expect, go away. Sorry. I expect, see, I forgot to do this today. Probably about a page or so, maybe at most 2 pages for the intermediate report. By October 23rd, you are probably going to have barely scratched the surface of the paper. You would have been able to figure out, some answers to maybe this question a little bit. You would have figured out a little bit of an answer to this question. You may, this might be hard, you may have got some very, very rough idea about how this paper is structured. I would like to hear what you have to say about that. The point of the intermediate report is not to, the evaluation of the intermediate report is going to be light. I want to merely say that you have something there. It is a way of checkpointing to make sure that you don't wait till the last minute to do anything. Because as you can see with these kinds of things, if you wait till the last minute, you're going to not be able to produce anything reasonable. This is a kind of a way to encourage you to start thinking about this now. But I fully expect that you're going to get only a part of the way into it. You're not going to get much. So I will put out a bit more detail on what I want in the intermediate report of a particular format. But it will be basically 1 to 2 pages, and it will just have some rough answers to these questions. Okay? No? Yes?
So for an intermediate report, if we're struggling to understand something and like we need help, can we just mention that in the report?
Yes, absolutely. Absolutely. Yeah. I will be reading all these reports and I will, and again, come and talk to me or post some, for some specific thing that seems more generic, you can post in discussion, or you can post a discussion anyway. I can answer it anyway, so it's fine. Yeah, the intermediate report is a good point, good place. It's a good checkpoint for you to identify things you are just completely stuck on and try to sort of see where you're stuck on and make a list of them. And that if you spend some time reading the papers, you will get to that point. Okay, so try to make a list of those things and add them in. That will be helpful as well. Okay, I will see you all on Thursday.
Yeah.